Greetings. So we should be approximately here on the schedule. You'll have listened to my intro, which I gave in a live workshop as a follow-up to the lecture from Steve that you heard in yesterday's individual session. In the live workshop, we jumped straight from the intro to constructing a model. In this case, we're going to construct the model with you interactively on Tuesday, but I'm going to do some of the discussion now to keep the flow of the workshop going. So you can find this video here, which you've presumably already done, but I'll remind you I also have handouts for you to use to take notes if you like, or draft slides for you to follow along or jump back and forth or review the lecture. So we talked about conceptually constructing an ODE implementation of our conceptual model. And we'll talk more about this in terms of our model taxonomy. When you create a model, you have choices. In this case, I'm focused on the choice between continuous time, which is conceptually the simplest, and discrete time, which is often the simplest to implement. And that's what we're going to implement in the spreadsheet for the sake of interactive simplicity. Both of these involve deterministic models. Both of these are models that will do the same thing every time you run them with the same parameters, as opposed to stochastic models, which imagine that there are some random factors that influence your model but are not explicitly coded in it. And I'll mention too, we'll come back to this when we do a deterministic model, we basically need to treat individuals as continuous and not discrete. I'll get to that at the end of this lecture. So when we make an ODE or other simple model, it's worth thinking about what assumptions we're making and how they might affect our conclusions. So this is an amazing object. This is a lab beaker that has a little lozenge spinning inside it at amazing speed, and it's mixing this solution very rapidly. And in my mind, this is a very good metaphor for what we assume when we do an ordinary differential equation model, because there are 10 to the 24th or more molecules of water here. So we have no problem assuming that that's a very large number and that maybe we can take a deterministic average, and the molecules of water are extremely well mixed. And these are two of the really basic assumptions we make when we put people into compartments, as we do for an SIR model, and assume that the compartments are smooth and uniform. Another assumption that we make when we do an ordinary differential equation is to say that my probability of leaving the infectious class, or my probability of dying at random, or my probability of moving, say, from exposed to infectious, we assume all of these things are memoryless, that the only thing that affects my probability of leaving a box is whether I'm actually in the box. And this memoryless assumption, which is conceptually simple, leads to exponential distributions for the amount of time that it takes to leave a box once you. And this is really can be a strikingly unrealistic assumption. It's come up, exponential distributions have come up recently in discussions of COVID modeling. For me, the most vivid example of what an exponential waiting period is if you think of human lifetimes. And the early models I learned on assumed that humans had lifetimes that were exponentially distributed with a mean of about 70 years, which means that given how flat these distributions are, we were assuming that 5% of everybody who was born would live for over 200 years, which is of course very unrealistic. But while we want to note the unrealistic assumptions that our models make, we don't necessarily throw out a model just because a specific assumption isn't realistic. As we'll talk about later, we want to figure out how our assumptions relate to our conclusions and which simplified assumptions might be good enough for the scientific question that we're asking. I'll talk a little bit about modeling using spreadsheets, which is what I'm going to do for you in our next interactive session, versus scripts. I like spreadsheets pedagogically. A lot of people are used to them and you can look at them very concretely. In the long term, for doing serious work, I would argue that scripts are better. There's about the same amount of information in this panel as there is in this panel. They both describe the fundamental flows of a model, but this panel has a lot of redundancy, a lot of hidden information. It's much easier to make a mistake here and much harder to find one. In either case, but especially if you use spreadsheets, it's really worth learning and thinking about best practices. So if you are going to do a model with spreadsheets, there are ways to do it better and ways to do it worse. And if you're working on an important problem, you want to be very careful. There are famous recent examples of horrendous mistakes hidden inside spreadsheets behind important science. Spreadsheets may be more intuitive for some of us, and for some simple problems, you may be able to check your spreadsheet exhaustively, and it might be the best way to do it and then immediately communicate it to somebody who might not be as into modeling as you are. I want to talk a little more about transmission and about how and when we break down beta, which you'll remember is our effective contact rate, into a product of rate of contacts and the probability that a contact will be infectious. So here's a contact that may or may not have transmitted influenza. It's got a child with a runny nose and another child reaching out to touch it. That's only one of a possible range of contacts we could imagine for influenza, right? I might wipe my hand on my nose and then shake your hand, or I might simply walk past you in a bus station. Both of these might be contacts. In either case, I might give you influenza, but first of all, it's hard to figure out how to count all these possible contacts. If I ride on a bus with you, did I contact you or not? And second of all, we don't expect them to have the same P. In a lot of disease modeling, we sort of avoid these questions by trying to estimate beta directly. In other cases, we don't. In other cases, if we're talking, for example, about the spread of COVID after it was recognized and protocols were in place, people might really be trying to count contacts. In the realm of sexually transmitted infections, there's a culture of trying to count contacts as bouts of sexual intercourse. You can argue about this, but for now, we'll say that sometimes it's useful to try to break down beta, our effective contact rate, into a contact rate and a probability, and that sometimes it's not. And I would say it's usually not clear. We can come back to this if people are interested, and we may discuss it more when we discuss heterogeneity. I also want to pick up on something that was a question during Steve's lecture from yesterday about how beta changes with population size and the two different formulations, beta SI and beta SI over N. And I think it really helps to think about physical interpretations of our model and about units when we do this. So we might assume, as Steve says, that as a city gets bigger or more crowded, that contact rates change, or we might assume that they don't. In the simple models that Steve introduced, he generally assumed that population sizes weren't changing. So in that case, it doesn't really matter for his model conclusions how beta would change with population size, because he has a closed population and he hasn't allowed population size to change. So how do we consider the question? In our original model, we just assumed that beta was a constant, and that assumption doesn't affect us if we don't allow n to change. If we want to think about what might happen if we allow n to change, I prefer to keep this formulation. I like to write beta this way, because in this way, as we've explained, as we've discussed, beta is a rate. It's the rate at which a susceptible or an infectious individual makes potentially infectious contacts. We've assumed them to be symmetric. So the way I add the possibility that beta can change with n is to simply write beta as a function of n, and then ask what would be the result of different assumptions about that. Standard incidence is the assumption that beta doesn't change as population size changes. And this gets us back to something that looks almost exactly like our original formulation. Another name for it is frequency dependent transmission. On the other hand, the other simplest assumption we can make is the one called mass action. And mass action incidence, we assume that as the population changes, as people get more dense, the contact rate changes exactly proportionally. And this is often parameterized with something called beta, but I don't like to call this number a beta at all because it's not a contact rate. And I'll talk a little more about that. But if we parameterize like this and make this assumption, we get back to something that looks like the mass action equations, where transmission is proportional to the product of S and I, which might be an appropriate assumption in some contexts. Once we think of things in terms of beta being a function of n, there's also another name for mass action. Once we think of things in terms of beta being a function of n, we don't even need to use one of the classic assumptions. We can think about what information do we have and what assumptions do we want to make. And maybe at low population densities, beta increases as people or as ibises become more crowded together. And maybe at high population densities, it doesn't anymore. And so this might be a more realistic assumption to make about how beta changes if we have large changes in our population size on the same time scale that a disease is spreading. I really like to think about questions like this in terms of units. Units can often add clarity and concreteness to a discussion. And in this case, to me, beta, as I said, is a very physical idea, the rate at which contacts are being made. And if we write the transmission in our model, the rate at which people leave I to go to N, the total rate, that has units of people per time. And we see that writing transmission in this form, I over N is a pure ratio, people over people, S is people. So that leaves beta as a pure rate, which is sort of what we expected it to be. It allows us to multiply beta by the duration of infectiousness. So the rate at which I'm making infectious contacts times the duration of my infectiousness gives me the reproductive number. So that's a beautiful formula. Here I'm putting 1 in square brackets to mean that it's a unitless as well as a beautiful quantity. If we use the alpha formulation and do a similar calculation, we find that alpha has units that are quite confusing. And I've seen smart people in fairly big papers get confused by the units of alpha. Sometimes you might want a model that uses alpha, but if you do, you want to think carefully about the units, and you might want to start with beta, a rate, and explain what additional assumptions you made to get here. So Steve talked to you about the idea of closing the circle, the idea that the model may give you just a single epidemic, or if we have a way to get recovered individuals back to the susceptible class, either directly or indirectly, we might get recurrent epidemics, which might oscillate or might simply reach an endemic equilibrium. And for this lecture, I'm just going to leave it open what mechanism I've put in here and what mechanism I've put in at the bottom. And if people are interested, we can talk about it in our interactive session. If I close the circle, there are actually interesting mathematical subtleties about possible differences between these two models, which we are going to neglect. When I close the circle, simple models have a strong tendency to oscillate, but also a weak tendency for the oscillations to be damped, to go away. So here's a model where I start with a lot of susceptibles and I get a dramatic epidemic at first, which looks like it's on its way to burn itself out. But because I've closed the circle, we get a smaller epidemic and then a smaller epidemic, and then a smaller epidemic. Steve has talked to you about the fact that if we add any sort of perturbation, he used the example of seasonality, to this tendency for the oscillations to get smaller and smaller, we often expect to see persistent oscillations. And so the disease system has this tendency, and it's a tendency very similar to one many of you might have seen in predator-prey systems, that if we have a lot of susceptibles, that's good for the infection, which leads to fewer susceptibles, which is bad for the infection, which can eventually lead to more susceptibles, and we get these sort of recurrent patterns. Seasonality can make these oscillations persist. Other kinds of perturbations can. And one of my favorite models is the model that makes the simplest possible version of the ODE model, with only the stipulation that we're going to treat individuals as individuals. And once we treat individuals as individuals, we find that there's no good way to make a simple deterministic model, because in our ODE model, we're saying, well, if I introduce one infectious person to the population, then maybe if R naught is greater than 1, then an hour later, there might be 1.05 infectious people and then 1.1 infectious people. Once we require these numbers to be whole numbers, there's really no simple, consistent way for saying, when does the number go up because there's an infection versus when does the number go down because somebody recovers. Even if we know what the next event will be, exactly when it will happen. And so the only simple way to incorporate individuality is with stochastic models. And once you add stochastic models, even to fairly large populations, here I've simulated a disease in a population of 100,000, the interaction between this randomness and the timescales of infection and recovery often leads to quite large oscillations. Remember, these oscillations are caused just by the fact that we've treated individuals as individuals, but the size of the oscillations because of these interactions is of the order of hundreds of individuals in terms of the increase and decrease in the number infected. And this is what I said I would get back to in terms of our taxonomy, that if we want to treat individuals discretely, we're more or less doomed to a stochastic model, a model that has more stochasticity, that has randomness in things that we're not able to model simply. And so we model that as random effects. So to conclude what I've been trying to tell you today, dynamic models are an essential tool because they allow us to link between scales. And we'll talk about the fact that we use dynamic models to link between scales in two directions. We use dynamic models to try to understand population scale data and what it means for individuals. And we use dynamic models to ask what happens if we make an individual level intervention. What do we expect it to do to a population? There are many ways to construct and implement dynamic models. Don't be intimidated by people who are more mathy than you, or people who say, why didn't you use an ODE? Or why did you use an ODE? Don't be intimidated by the fact that ODEs look like differential equations. As Steve said, it's just a simple way of describing the rate at which things are changing. Very simple models provide us with useful insights, like the fact that we have thresholds for a disease to increase, like the fact that we can think about disease in terms of basic reproductive numbers and effective reproductive numbers, and like the fact that simple disease systems have a natural tendency for oscillation and a natural tendency for the oscillations to get smaller. That second tendency can be easily counterbalanced. More complex models can provide more detail, but also require more assumptions and more choices. And that's why we have to take the steps in Julie's world, where we move from the real world to the model very carefully. And whatever happens, the more we understand the simple principles we learn from simple models, the better we're going to do at navigating. I'll talk to you all soon in person.